Hello, everyone. On behalf of my collaborators both in US and China, I would like to give a talk, BGC-Argo observations and the physical-biogeochemical modeling in the North Pacific Ocean. Here's the outline of my talk. First is the China ongoing activities and plans for the BGC-Argo, and I will use the BGC-Argo observations to illustrate how biogeochemistry responds to extreme weather events, in particular typhoon and winter storms. I would like to show the physical biogeochemical modeling and the forecasting scales for the Northwest Pacific Ocean, focusing on nutrients and plankton dynamics. Lastly, how we can incorporate BGC-Argo observations on autonomous platforms and the operational modeling aspect. For the last 3 years, the Second Institute of Oceanography in China has established a BGC-Argo observational network in the Northwestern Pacific. So far, we have deployed a 12 BGC-Argo float in the region. By the end of this year, there will be 6 more BGC-Argo floats deployed in the region. That will make a total 18 floats for the area. All the data are shared in real time through the international BGC-Argo network. In the September 2018, right after we deployed several BGC-Argo in the region, there are 2 Category 5 typhoons hit the area. We adjusted the sampling frequency right before the typhoon hit the area, and from 5 days to daily profiling, so we captured the response of upper ocean biogeochemistry to typhoon. Here's the trajectory of Typhoon Trami, the end of the September, and then one of our BGC-Argo float location. As you can see, that BGC-Argo captured the daily profiles of surface chlorophyll on a daily basis and shows the increase by about a factor of 3 during the peak of the typhoon. Yet the remote sensing only picked a few of the chlorophyll response in the surface because the cloud coverage. We also use the profiles of the BGC-Argo chlorophyll, showing that mixed layer prior to the typhoon is only about 30 meters. During the peak of the typhoon, the mixed layer increased to about 100 meters. In the top 50 meters, the BGC-Argo measurements showing all the chlorophyll increase from factor 2 to 3. Below the 50 meters, especially the subsurface chlorophyll maximum, showing a significant decrease. If you integrated a chlorophyll from surface down to 150 meters, there is no net biomass increase, that whether it's a chlorophyll or a POC from the backscattering measurements. So that indicate this is a purely redistribution of chlorophyll from subsurface to the surface. There is no new biomass generated. Here's the summary of the limited response to typhoon in terms of the phytoplankton dynamics in the region. The upper 50 meters phytoplankton showing the increase, the deeper chlorophyll maximum showing the decrease, and the integrated chlorophyll from surface down to 150 meters does not change, so indicate there's no new phytoplankton biomass generated due to the typhoon. This is mainly because high nutrient waters tend to be deeper than 100 meters. That's the mixing depths that typhoon can reach. So no nutrients bring to the euphotic zone. Therefore, there is no new biomass generated due to the typhoon. After the typhoon, we kept this float doing the daily profiles for a total 9 months. And this particular float, 2750, caught in this Shikoku recirculation gyre, which is about 200 to 300 kilometers in diameter for 9 months. They do the daily profile throughout the winter. In particular, this floats in the stationary caught in this recirculation gyre. Throughout the winter, we can see there's many features, especially for the chlorophyll that is in increase in response to the mixed layer shoaling on the 8 to 10 days frequency. Whenever there is mixed layer shows, the chlorophyll increase in the region. When the mixed layer deepens, the chlorophyll decrease. This frequency is related to the winter storms passing through this area. Through January through March, we have captured a total 6 such winter events. That is, when the storm passing through the area, the mixed layer deepens from, say, 30 meters down to 150, even 200 meters. And then when the storm passes, the mixed layer shows to about 30 meters or so. The increase of the mixing is mainly through the wind. Whenever there's a strong wind, the mixed layer deepens. The shoaling of the mixed layer primarily due to the positive heat flux that is increased stratification at the surface rather quickly. Beside the chlorophyll response to the winter storms, the POC also respond to the winter storms pass through the region. During the shoaling of the mixed layer, the POC is generated in the mixed layer depths. During the deepening of the mixed layer, the POC exported to the depths, even can see down to almost 400 meters. This is a termed as a mixed layer carbon pump. Through the January to March, we have caught a total 6 times such of mixed layer carbon pump if we do the daily profiles. That total carbon export is about 8.9 to 7 grams carbon per square meter in this region in response to those 6 storms. If we do every 5 days sampling, and then we only get a fraction of this winter storm. We only caught 1. So the total carbon export is 1.25 grams carbon per square meter. If you do 10 days sampling, we completely miss the winter storm's response, this mixed layer carbon pump. To summarize this mixed layer carbon pump and the typhoon response. So we have the BGC-Argo float provide global coverage, but we need to consider this temporal sampling strategy to capture biological and then biogeochemical response. So the daily profile showing the typhoon and the winter storms in the Northwest Pacific. Again, the mixed layer depths, that is really redistribution of the chlorophyll maximum from the surface, from the depths to the surface. And then the winter storms and also showing this a mixed layer carbon pump can be significant. Currently, the most of physical biological models do not capture those synoptical the weather events. So we need to consider how those extreme weather events and impact on the biogeochemistry processes in the model. Because of this float reached at the end of May, reached to about 200 profiles, and then it's almost at the end of this float battery life. So we work with a Chinese fishing vessels in the area and then send exactly the location of the floats and stop a profiling, and a captain of the fishing boat recovered this float for us in about extra 6-7 hours of work. So I think this is also the future direction, how we can use various research and the fishing vessels and the sea to recover the BGC-Argo floats. For the past 20 years, we have been working for Pacific basin-wide physical biogeochemical modeling. The circulation model is based on the regional ocean model system, ROMS. The ecosystem model is based on carbon, silicate, nitrogen ecosystem model called cosine. This model is high resolution, 1/8 of degree for the entire Pacific. We run this model from 1991 up to present. That gives us the seasonal dynamics, the interannual variability, as well as a decadal variability for the North Pacific. For this presentation, we focus on the Kuroshio Extension region in the Northwest Pacific. In this region, the different water masses meet and then also create this very complicated eddies and front in this region. And sometimes it's very difficult to observe such a mesoscale and sub-mesoscale processes, especially for this long-term changes. For this Kuroshio extension region based on Baoqiu, they separate into two modes. One is the stable mode, one is the unstable mode. During the stable mode, the Kuroshio extension is intensified, and then they move to the north, and then the path is a clear, defined. During the unstable mode, the Kuroshio extension jet reduced a eastward transport, and the north-south the direction is more pronounced. So they are lasting from 2 to 4 years for each mode, and then they switch. Based on the remote sensing information, we look at a Kuroshio extension region that during the stable mode, the chlorophyll decrease, and then during the unstable mode, the chlorophyll increase and roughly about a 20% the magnitude change. Such a change is mainly caused by the large scale, the Pacific dynamics. In particular is the PDO and then the North Pacific Gyre oscillation, NPGO. So this has about a 3 to 4 years lag. The NPGO is the second mode of the EOF analysis of sea surface height. Through this Rossby wave dynamics, that the signal propagate from the eastern Pacific all the way to the western Pacific coastal region and then affecting the nutrients and the plankton dynamics. As you can see, during the stable mode in the 2002 through 2005, the sea surface height in this region increased. From 2006 to 2010, the sea surface height in this region actually decreased. And then correspondingly, during the stable mode, the chlorophyll decreased. In the unstable mode period, the chlorophyll in this region increased. This is the model can capture both sea surface height dynamics as well as the chlorophyll response. The correlation between the modeled sea surface height anomaly and then surface chlorophyll anomaly between the model and the observed is relatively high. To further examine the stable and the unstable mode dynamics in this region, we compared observations and then modeled the results. The first panel shows during the stable mode, sea surface height anomaly increase. That's both in the observation and the model in this region. During the unstable years, that sea surface height in this region decreases. To amplify this contrast, we subtract the stable years from unstable years to make this comparison. As you can see, in the crucial region, this is well pronounced both in the observation and then the modeled results. We further follow this approach to compare the modeled phytoplankton and the zooplankton biomass in the top 100 meters integrated, compare the unstable mode versus the stable mode. As you can see, the difference between the unstable and the stable mode is well pronounced, both in the phytoplankton biomass as well as in the zooplankton biomass in this region. We further look into the modeled dynamics, how the phytoplankton and zooplankton respond to this stable and unstable mode. This is the vertical profiles of the temperature and nitrate in the Kuroshio Extension region. As you can see, in the stable years, that during the winter, the nutrient and the thermocline deepens. And then during the unstable years, the nutrient and the thermocline shallows, especially during the winter. The black line is the mixed layer depths. If you do a lead correlation of 200 meters temperature and 200 meters nitrate with NPGO, there is a well pronounced from the east to the west propagation with a 2 to 4 years delay, which is indicated as the Rossby wave propagation in this particular latitude. This correlation is also well pronounced with the a 17-degree temperature depth and 6 millimoles cubic meter nitrate concentration. The correlation is extremely high. That's between the negative 0.6 to the positive 0.6. If you correlate with the modeled integrated phytoplankton and the zooplankton, it shows the similar correlation, that is 0.6 negative to 0.6 positive. This gave us a indication that we may have some predictability on the decadal time scale, that 2 to 4 years, the changes for this region, not only the nutrients and temperature, but also the phytoplankton and the zooplankton. To summarize the modeling results for this region, the interannual variation of the biological processes in the Kuroshio Extension region are mainly influenced by the remote perturbation NPGO. This region, from the physics to the phytoplankton, is lag NPGO by about 2 to 4 years. During the stable years in the winter, the nutrient climb deepens, the upper layer nutrient decrease, which results in the spring phytoplankton biomass decrease, vice versa for the unstable years. In order to test and prove this model results, we will need more observations, especially the BGC-Argo floats, the coverage for this region. If we have a larger spatial coverage to resolve this east and west connectivity and more temporal profiles during the winter period and the spring period, we may have a chance to make this 2 to 4 years forecast and for this region from the thermocline, nutrient to the phytoplankton and zooplankton biomass with a 2 to 4 years lead time. The last topic of my presentation is really how we use the BGC observations on the autonomous platform, not only the BGC-Argo, but gliders and surface observational networks. So this is the ocean remote sensing color, and then this is the BGC-Argo. We will have to combine the BGC-Argo and then with remote sensing and work in synergy together to give a four-dimensional view of ocean biogeochemistry. A group of us worked together for about a year to write this perspective. It's really not only for the BGC-Argos, but the other autonomous platforms, because the other autonomous observing platforms, such as gliders, wave gliders, and the sail drones, they all equipped with the similar biogeochemical or optical sensors on them, such as dissolved oxygen, nitrate, and chlorophyll, CDOMs, and etc. If we put all this together, and then that will give us a much better the temporal and then a spatial coverage, but also the regional coverage. The BGC-Argo gave us the one-dimensional profile on the global basis. The gliders can cover the coastal regions. The sail drones can cover the surface and hard-to-reach areas such as the Southern Ocean and the areas. So you'll have to work in the synergy, put all those observations into the model. So here's the summary slides of this particular perspective, that how we can combine various observational information from satellite research vessels and the autonomous platforms, the BGC-Argo, sail drones, wave glider, etc., and into the model, and then through this data simulation, but also the feedback from the model back to the observations to refine the observational assets allocation, and then also the temporal and the spatial coverage of the different platforms. So through this loop, we can further improve the models, improve and most effectively use the different observing assets. With that, I stop. Thank you.